Last month, the world fixated on interstellar comet 3, I/Atlas gliding harmlessly by Earth. But almost no one noticed the real threat. A 100 times bigger cosmic beast, C/2025 R2, slipped into the solar system undetected, concealed in the sun's blinding glare. It was only found after its closest solar approach, using a space-based hydrogen imager, too late for ground telescopes to sound the alarm. In just 7 days, this monster will sweep closer to Earth than any major comet in memory. The danger isn't a Hollywood impact, it's what we failed to see and how debris, fragments, and blind spots could trigger consequences we haven't even anticipated. How did we miss it? And are we ready for what comes next? On September 11, 2025, a faint ultraviolet glow caught the attention of Vladimir Bezugli. He was scanning data from the Solar Wind Anisotropes instrument, SWAN, aboard SOHO, a spacecraft that spent nearly 3 decades watching the sun's outskirts. The image showed a hydrogen cloud expanding in a direction no one expected. Within hours, the SWAN team flagged it as a possible comet. Ground telescopes scrambled to confirm, but the object was still hidden in the sun's glare, invisible to every optical survey on Earth. Only SOHO's ultraviolet eyes, sensitive to the hydrogen streaming off icy bodies, could reveal what was there. By the time the discovery circled through official channels, the comet had already passed its closest point to the sun. Bezugli's find was named C/2025 R2, SWAN, the 20th comet credited to this aging space-based watcher. Its hydrogen envelope stretched across millions of kilometers, signaling intense outgassing and rapid brightening. For astronomers, this was both a triumph of persistence and a reminder of a glaring vulnerability. Without SWAN's ultraviolet imaging, the comet would have slipped by, unseen, until it was far past perihelion. Most of the world's telescopes had been staring at the wrong patch of sky, blinded by the sun's brilliance. The discovery didn't just belong to one observer or one instrument. It was the product of a system built to catch what ground-based eyes cannot. The question now wasn't just what SWAN was, but how many more giants like it might be hiding in the light. The sun's glare carves out a blind zone that has haunted astronomers for over a century. This region, known as the Holacek effect, covers the slice of sky within about 30 degrees of the sun, an area where no ground-based telescope can reliably search for comets or asteroids. During these weeks, even the most advanced optical surveys are powerless. Twilight washes out faint objects, atmospheric scattering turns the sky opaque, and the very geometry of Earth's orbit means anything approaching sunward remains hidden until it swings away from the solar disk. Between August and mid-September 2025, C/2025 R2 moved through this invisible corridor. From our vantage point, the comet was buried in daylight, its rapid brightening entirely masked by the sun's overwhelming light. The Holacek blind spot isn't a glitch in technology, it's a fundamental limit set by physics and geometry. Even the largest, brightest objects can slip through undetected if they approach from the wrong angle. Space-based instruments like SOHO's SWAN camera are the rare exceptions. By observing ultraviolet emissions from hydrogen, they can spot comets in the very places Earth-bound eyes can't reach. But SWAN's field of view is limited, and its aging detectors offer only a patchwork glimpse of the threat zone. The reality is stark. For nearly a month, a long-period comet streaked toward the inner solar system, its outgassing and dust eruptions invisible to every major survey on Earth. The Holacek effect doesn't just hide the faint and distant, it can cloak giants until they're already among us. Each object lost to the sun's glare is a reminder that our watch on the cosmos has blind corners, and that the next warning may come only after the danger has passed. On September 12, 2025, C/2025 R2 reached its perihelion, its closest point to the sun, swinging in at 0.503 astronomical units, or about 75 million kilometers from the solar furnace. This is the moment every long-period comet dreads and astronomers anticipate. The instant when centuries of cold storage end, replaced by a surge of solar energy that can transform a quiet traveler into a spectacle or a casualty. At this distance, the sun's radiation ramps up by a factor of 4 compared to Earth, driving surface temperatures on the nucleus well above the freezing point of water. Layered ices, some untouched since before recorded history, begin to sublimate violently. The result is a pressure cooker effect, with jets of gas and dust erupting from weak spots and fractures, feeding the expanding coma and tail. Thermal stress at perihelion can crack open old comets, especially those returning after thousands of years in deep freeze. For C/2025 R2, the perihelion passage was both a trigger and a test. The comet's hydrogen envelope ballooned, signaling a spike in water production as solar ultraviolet light broke apart molecules streaming off the surface. Observers tracking the event noted the rapid growth of the coma, but the nucleus itself remained shrouded. No resolved core, just a bright, unresolved point at the heart of the activity. With the sun's glare still masking direct observation, any sudden outburst or fragmentation would go unrecorded until the comet emerged into darker skies. Perihelion isn't just a milestone on the orbital path, it's a crucible that determines whether a comet survives intact, sheds fragments, or disintegrates entirely. For C/2025 R2, what happened in those hours near the sun would shape every unpredictable behavior that followed: outbursts, dust jets, and the potential for debris to scatter along its path. The real story of this visitor's volatility began the moment it crossed the perihelion line. On October 20th, 2025, C/2025 R2 will pass just 0.2606 astronomical units from Earth, roughly 39 million kilometers, or about 101 times the distance to the Moon. For a comet of this size and brightness, that's not just close. It's a statistical outlier, the kind of flyby that happens once in centuries, not decades. But proximity alone doesn't tell the whole story. The minimum orbit intersection distance, or MOID, measures the smallest gap between Earth's orbit and the comet's own path. For SWAN, that MOID sits at 0.048 astronomical units, about 7.2 million kilometers. In cosmic terms, that's a near miss. It's well within the zone that planetary defense teams use to flag potentially hazardous objects, even if the actual risk of collision is zero this time around. The numbers demand context. Mars, at its closest, comes within about 56 million kilometers of Earth. SWAN's flyby slices inside that, threading the gap between our planet and the orbits of our nearest neighbors. For comparison, the much-hyped interstellar Comet 3, I/Atlas, never gets closer than 1.8 astronomical units, over 270 million kilometers. SWAN's approach is more than 6 times nearer, and it's happening in the same week. The ticking clock isn't about impact. It's about what can be learned and what might be missed during these few days of closest passage. With the comet's trajectory set, the real urgency comes from its behavior. Outbursts, jets, and the potential for unseen fragments all become more critical as the distance shrinks. The MOID isn't just a number on a chart, it's the dividing line between a harmless flyby and a debris stream that could sweep through Earth's neighborhood. Every kilometer matters. As October 20th approaches, astronomers are racing to collect every possible data point. The window for high-resolution imaging, for tracking sudden changes in brightness, and for mapping the dust environment is narrow. Once SWAN recedes, the chance to study a long-period comet at this range won't come again soon. The clock is running, and the stakes ride on how much can be captured before the moment passes. Late September brought a jolt no one could model. Comet C/2025 R2's brightness, which had tracked a slow decline after perihelion, suddenly surged by more than a full magnitude in less than half a day. Observers in the southern hemisphere logged the jump first. What had been a faint smudge in wide-field images now rivaled the dimmest stars visible to the naked eye. The comet's coma, already expansive, took on a vivid green cast, a telltale sign of C2 and Cn molecules fluorescing under solar ultraviolet. That color, familiar to comet watchers, signaled intense molecular activity, a chemical flare-up as buried ices vaporized and rushed outward. Jets of dust and gas began to fan out from the core, carving transient arcs and streaks across the coma. The geometry of these jets shifted hour by hour, hinting at a spinning, possibly tumbling nucleus beneath the haze. Yet no telescope, not even the largest on Earth, could resolve the core itself. The nucleus remained a pinpoint, masked by the glare of its own outgassing. Every attempt to catch a fragment, some secondary shard or companion, came up empty. If the late September outburst had cracked the nucleus, the evidence was buried in the dust, invisible to all but the most sensitive instruments. The unpredictability extended to the comet's light curve. Forecasts that put SWAN at magnitude 6 by October were overtaken by reality. The comet hovered between 6 and 7, with wild swings each night. Amateur astronomers debated whether they were seeing fresh outbursts or just the play of sunlight on ejected dust. The truth was, no one could say for certain. Dynamically old comets like this one carry scars from previous solar encounters, fractures, depleted reservoirs, pockets of volatile ices waiting for the right moment to erupt. Each outburst rewrote the script, and every spike in brightness raised the specter of fragmentation. The green coma, the erratic jets, the unresolved nucleus all point to a body in flux, its future behavior impossible to pin down. For those tracking potential hazards, this is the nightmare scenario. A large active comet, close to Earth, with a history of unpredictable outbursts and no clear sign of structural integrity. The only certainty is uncertainty, and with every new image, the question grows sharper. What, if anything, is hiding inside that cloud of dust and light? C/2025. R2's orbit reads like a cosmic warning label. Its path is stretched to the edge, an eccentricity of nearly 0.999, a period that spans over 22,000 years and an inclination of just 4.5 degrees above Earth's orbital plane. That geometry is anything but random. Most long-period comets slice in at steep angles, spending only hours or days near the ecliptic before vanishing back into the deep. SWAN, by contrast, lingers in Earth's lane for weeks, crossing the same celestial highway where planets and satellites travel. The odds of such a massive active body threading this corridor are slim, but the consequences ripple far beyond the numbers. Every outburst, every jet of gas, acts like a miniature thruster on the nucleus. The physics is relentless. Sunlight pounds the surface, ices vaporize, and jets erupt, pushing both dust and the core itself off their predicted paths. For a comet this active, the non-gravitational forces aren't just a footnote, they're a wild card. Since perihelion, astrometric fits show a drift of about 1,000 kilometers from the expected trajectory, a direct imprint of outgassing thrust. For small fragments, the effect is even sharper. Radiation pressure and gas drag can fling millimeter to meter scale debris onto diverging tracks, seeding a diffuse stream that stretches along and away from the comet's path. These particles don't vanish. Over days and weeks, they spiral outward, forming a broad ribbon of dust and microfragments. Earth's orbit sweeps through this region every year, but in 2025, the alignment is uncomfortably close. Even a diluted stream, packed with particles too small to see, can spike the background rate of meteoroids. For spacecraft in low Earth orbit, a few extra impacts per square meter can mean degraded solar panels, pitted sensors, or, rarely, catastrophic failure. The risk isn't a Hollywood impact, it's the silent statistical threat of micrometeoroid flux, invisible until something stops working. Historical analogs show how fast the environment can change. Comet 73P/Schwarzmann-Wachmann 3 shattered during a close approach, and its debris field peppered Earth with meteors for years. SWAN hasn't split, at least not yet, but its erratic outgassing and unresolved nucleus keep the possibility on the table. Each new jet, each unmodeled drift, is a reminder that the physics of comets doesn't end with their orbit. It extends to every fragment, every grain of dust, and every spacecraft caught in the crossfire. The question now is not just where the nucleus will go, but where its debris will land, and how ready we are to see it coming. October 2025 delivers a sky so crowded, even seasoned astronomers find it hard to keep their priorities straight. Comet C 2025-R2 is not the only comet lighting up the charts. C 2025 ACE, better known as Lemon, is climbing in brightness, promising a binocular show of its own just as SWAN hits its closest approach. At the same time, the Orionid meteor shower peaks on the night of October 21st, sending streaks of Halley's debris across pre-dawn skies. For the public, it's a celestial festival. 2 comets visible in the same week, meteors flashing overhead, headlines full of superlatives. But for those tasked with monitoring real risk, this convergence is a double-edged sword. The spectacle draws eyes upward, but it also splits attention. Outreach campaigns focus on where to look and what to photograph, while the subtler hazards, debris streams, fragment drift, spacecraft exposure, fade into the background. In a week packed with cosmic attractions, the challenge isn't just seeing what's out there, it's remembering which threats demand vigilance and which are only distractions. The official discovery of C/2025-R2 triggered the standard reporting chain. Minor Planet Center, JPL Horizons, then CNEOS. Each step in this pipeline relies on data from the last, and every link has its own friction points. The Minor Planet Center collects initial astrometry, often within a day of confirmation, but for comets like SWAN, that data starts thin. Just a handful of post-SWAN detections, all after perihelion, with a nucleus still unresolved. Horizons computes preliminary orbits, but with a short observation arc, uncertainty balloons. By October 13th, orbital fits still depend on just 3 weeks of tracking, and non-gravitational forces, outgassing, jets, subtle nudges, can push the predicted path by thousands of kilometers. CNEOS, the endpoint for risk assessment, does not even open a case file unless the numbers suggest a credible threat. For long-period comets, the policy is hands-off. That leaves gaps in real-time alerting and risk modeling, especially when outbursts or sudden brightness jumps force manual review. Each orbit update requires human oversight, not just for accuracy, but to spot the unpredictable. With instruments like SOHO's SWAN aging and calibration drifting, the pipeline faces a single-point failure risk. One detector, decades old, standing watch over the sun's blind side. The system is robust on paper, but in practice, late discoveries like SWAN reveal just how much depends on luck, timing, and a handful of overworked eyes. Small asteroids have a way of slipping through the net. In 2008, TC3 was spotted just 19 hours before it burned up over Sudan. 5 years later, 2014. AA entered Earth's atmosphere with barely any warning at all. Even in 2019, asteroid MO was detected only hours before it exploded south of Puerto Rico. The lesson is simple. Approach angle and sun glare can erase days or weeks of warning, no matter how advanced the survey. Comets add another layer of unpredictability. In 1990, 73P/Schwarzmann-Wachmann 3 broke apart during a close approach, scattering fragments and dust that peppered Earth's skies for years. What these cases share is a vulnerability. Objects discovered late or fragmented unexpectedly leave little time for response. The checklist now is clear. Update orbital predictions daily as new data arrives. Push for high-resolution imaging to catch fragments early. Coordinate wide-field monitoring for dust and meteoroid streams. Share real-time satellite impact logs and meteor radar data. Invest in sunward-facing telescopes, not just ground surveys. And above all, build public dashboards that keep the risk visible, not just the spectacle. Each late find is a reminder. Vigilance is the only defense when the sky's blind spots are this wide. On September 11, 2025, Comet C/2025-R2, also known as SWAN, was discovered just 1 day before its closest approach to the Sun, evading ground-based surveys due to the Holacek blind zone. Unlike the widely discussed 3I/Atlas, SWAN will pass within 0.2606 astronomical units, about 39 million kilometers, of Earth on October 20, 2025. Archival data confirm no direct impact threat, but the late discovery and unpredictable outburst underline a systemic blind spot in our detection pipeline. Past cases like 2008 TC3 and 2014. AA show that hazardous objects can be found with little warning, and the 73P comet breakup remains a cautionary example for fragmentation risk. Today, the true risk is not the comet itself, but the limits of our monitoring, especially for sunward arrivals. As the sky grows more crowded, frequent updates, targeted observations, and investment in sun-facing telescopes remain urgent needs. The story of C/2025 R2, SWAN, is a reminder that the next surprise may already be on its way, hidden in the glare, waiting to be seen.